All right, what we're going to try to do is work the pivot lab, but from the chemical standpoint of all the work that we need to do behind. So like the behind the scenes of what's actually happening in the pivot lab. In the pivot lab, you're given a single displacement reaction, and in which case we're given copper and silver nitrate is going to make copper 2 nitrate and silver metal. So what that's going to look like is, and I'm going to kind of read it, copper, which is Cu, and silver nitrate. Silver is Ag, nitrate is NO3. You can verify the charges of each on a polyatomic ion chart. The charge for silver is positive, the charge for nitrate is negative. Makes, in this case, when it makes it, it's introduced by water, or when water is introduced into the two different substances. Copper 2 nitrate, copper, nitrate. That 2 plus 2 is from these Roman numeral 2 right here. And silver. Should give myself more room. And silver. All right. So the first thing we want to do, once we've written this out, we now have our chemical equation. We want to balance out any bonding that's going on. Right now, copper metal is by itself, so it's not bonded, but we can say it's a metal, so it's a solid for S. Here we're going to say it's silver nitrate. It's also a solid. In this case, it's a solid, like it looks like a sugar. Looks like a sugar doesn't mean it is sugar. But we're going to say S for solid. When we mix it with water, we now have our first ionic bond and our first element that we need to balance out. Is meaning this is going to give off 2 electrons. Again, the plus 2 is from this 2 right here. Nitrate still remains a negative as it did earlier. If this can only accept 1 electron, that means we need 2 nitrates to accept both electrons. So this 2 is going to be written on the outside as a subscript number. That subscript number 2 tells us 2 nitrates are involved to balance out the 1 copper. Because there's only 1 here, we can imagine there's a 1 here as well, but we don't have to write it down. Due to the fact that we're mixing in water, the whole thing is going to be aqueous, meaning in an aqueous solution, water-based, and we're going to end up with silver metal, a solid. Now our next goal is to balance out the entire equation. So we have copper, silver, and then I'm going to keep nitrate the same because nitrate is within parentheses, this polyatomic ions within parentheses, so we want to keep it as 1. And I'm going to count how many is on each side. I write it in the middle so that way I can see going from side to side from my reactants to my products. And it should balance out due to the law of conservation of matter and the law of conservation of mass. I have 1 copper, 1 silver, and 1 nitrate. I have 1 copper, 2 nitrates, and 1 silver. So I need to balance this part out. Well, I can't add a 2 here because the subscript number is to try to balance out what's actually happening with the number of electrons. But what I can do is change the mole number. The number in front is going to be our mole number. It's going to allow us to balance out the entire equation. If I need 2 nitrates, then I need 2 nitrates. 2 nitrates, but that also means I have is 2 silvers. So if I put a 2 here, that'll balance out that silver as well. Now the whole thing's balanced, and I can put a 1 in front. Now again, you don't have to put the 1, but for right now, having a 1 there is good practice. And this is going to be our mole ratio throughout. So in other words, 1 mole of copper is needed for this reaction, and it's also going to be related to 1 mole of copper nitrate. Or 1 mole of copper in the reaction is related to 2 moles of silver, and vice versa. 2 moles of silver nitrate to 1 mole of copper nitrate, 2 moles of silver nitrate to 2 moles of silver, or 1 copper and 2 silver nitrates is the mole relationship. So again, these are the mole numbers. The mole ratio is the best way to put it. The next thing we want to do is find our molar masses. And we're just going to find the molar mass of copper, all of them. Actually, finding them all would be good practice. To find the molar masses, we need a periodic table. 1 mole of copper is equivalent to 63.546 grams. Where am I getting that number from? Here. 1 mole of silver is equivalent to 107.868 grams. Here's where it now gets a little bit complicated because now we're dealing with more than one element. So for silver nitrate, 1 mole of silver nitrate means I need 1 silver, 1 nitrogen, and 3 oxygens. The mass of silver is 107.868. The mass of nitrogen is about 14. And the mass of oxygen for 3 of them is 48. How do I get that? Mass of oxygen is 16. 16 times 3 is 48. I'm then going to add it all together, and I'm going to get a molar mass of silver nitrate to be 0.868, 15, 19, 169. 0.868 grams. Keep in mind this is an estimate. Why is it an estimate? It's going to depend on which numbers and how many decimal places you use. But if you get about 169.868, you're on the right track. And I want to do the same for here, for copper nitrate. 2 of them. Here's where it gets interesting. 1 mole of copper nitrate is, I want to be sure that I have it all. So I'm going to take this math and I'm going to do the math here. So I have 1 copper. I have 2 nitrogens. And I have is 3 times 2 is 6 oxygens. 1 copper is 63.546. 2 nitrogens, 2 times 14 is 28. And then now we have the issue with 6 oxygens. So we're going to do is 16 times 6, and I believe that's going to be 72. 96, excuse me. 96. Add it all together. And the molar mass of copper nitrate is 187.546. So again, now we have taken the reaction of what's happening, we put it into an equation. We balanced out each bond by using ionization charges and crisscrossing when necessary. 1 and 1, 2 and 1. We then balanced out the entire equation using our mole ratios to balance it out. We also found out the molar mass of all the elements and compounds that we are dealing with. 1 mole of copper is 63.546 grams. 1 mole of silver is 107.86 grams. 1 mole of silver nitrate is 169.868 grams. And 1 mole of copper nitrate is 187.546 grams. And I'm going to pause the video and restart it, because now what we're going to get into is figuring out limiting reactants, and it's going to go heavily into stoichiometry. But these numbers, these molar masses, is going to help us out in how we're solving this. So now we're going to get into trial 4, which is the example that we used in class. You'll see that I have already kept and written down the mass of silver nitrate, I believe, was 15 grams, and the mass of copper. In class, we discussed how we had to measure the mass of the beaker. Then they're going to put in the silver nitrate, and it's going to be put into it's going to look like a sugar powder or white powder. Then you subtract the difference, and I believe our number was 15 grams. Then it's going to add water, and it's going to have its new mass. From there, to find out the mass of copper, is they're going to include the mass of the copper wire, and we're going to see it increase. Why does it increase? Due to the law of conservation of mass. And it increased by 1.51 grams, and that was just when it introduced copper. When you do trial 2, do the same type of subtraction in order to get these two given or starting off masses. Because now we want to find the limiting reactant by using stoichiometry. The first thing we want to do is we want to convert grams into mole. Because these are mole ratios, we can have a relationship into what we're solving for. And what we're solving for is silver. Why silver? Because we know that our product is going to be silver metal, and this silver metal is going to then be collected and measured at the very end of the experiment that you will notice in prediction part 3 in your pivot lab. So we know 15 grams are given, and we also know that 169.868 grams equals 1 mole of, again, silver nitrate. The grams cancel out. The next thing I want to do is now use my mole ratio. 2 moles of silver nitrate is equal to 2 moles of silver. So 2 mole of AgNO3 is equivalent to 2 mole of silver. This can cancel out as well. Now, we know that 1 mole of silver, because we want to find the mass, is equivalent to 107.868 grams. This is now going to tell us how many grams of silver we should have at the very end. The way we're going to do this is we're going to multiply everything on top and divide by the bottom number. So what I have is 15 times 1 times 2 times 107.868 equals, divided by 169.868 divided by 2 divided by 1, and that gives us an answer of about 9.52. So I'll put 9.5 grams of silver is how much we're expected to get if this holds up. But we're looking for the limiting reactant, because you can only make so much based on how many ingredients of what that you have. In the example that we used with Noemi, she was making mashed potatoes. Well, if she has an endless amount of mashed potatoes but limited milk, then milk is her limiting reagent. She can only make so much mashed potatoes based on how much milk she has. If she has an endless amount of milk and a limited amount of potatoes, then the potatoes are the limiting reagent. So we're looking for the smaller answer at the very end of the day. Now for copper. I'm going to put so many grams of copper. That is 63.546 grams of copper. That's equivalent to 1 mole. You're going to see a pattern. Grams cancel out. 1 mole of copper, 1 mole. We're looking for silver is equivalent to 2. 1 mole of copper cancels out is equivalent to 2 mole of silver. Then we can say at the very end, you're going to see the similarity, exactly the same. And we want to find out the mass. What we're going to do in this case is 1.51 times 1 times 2 times 107.868. Divide that by 63.546. And I'm going to get an answer of 5.12. Meaning, copper, because I produce the smallest amount of silver, copper is my limiting reagent. In other words, we have more silver nitrate than what we need, meaning based on the amount of copper that we have, we can only make 5.12 grams of silver. Thus, because the smaller of the two, copper is my limiting reactant in this procedure. Hopefully this helps out more. Try to do the same thing for trial number 2. And when we get back to class on Monday, we're going to go over the answers, what you should have gotten for trial number 2, so we can proceed forward with the experiment.